Okay, so hi everyone. I'm Peiyan Zhang from the Hong Kong University of Science and Technology. I'm pleased to welcome you to my presentation. In this presentation, we will explore how the concept of graph prompt tuning can be applied to streaming recommendation systems to enhance their performance and adaptability. So let's get started. We will start with some context about the current landscape of recommender systems. We'll then identify the key challenges faced by existing methods. After that, we will introduce the concept of graph prompt tuning and delve into the core of our approach and the evaluation. Finally, we will summarize our findings and discuss the implications of our work. In the modern recommendation paradigm, models are typically trained on static complete datasets and evaluated in a one-time process. However, this approach creates a significant gap when compared to real-world applications. In real-world scenarios, new interactions arrive continuously, introducing new data distributions that static models are not equipped to handle efficiently. This constant influx of new data poses several challenges. First, the new interactions arrive continuously. New data introduces new distributions, which the static models cannot handle efficiently. And updating models using new data risks overwriting previously acquired knowledge, and the models must be balanced, learning new knowledge while preserving historical context to avoid degrading performance on previously learned tasks. So now let's look at the existing continual learning methods and their limitations. The first is the experience replay-based methods, which periodically retrains the model using a selection of past samples stored in a replay buffer. However, their effectiveness diminishes with smaller storage sizes, and they are less feasible where strict privacy rules apply. For the regularization-based methods, they keep the model's parameters in check to maintain alignment with previously learned patterns. However, they struggle when new data greatly differs from past data, and they risk losing old knowledge if the parameters cannot adapt to new information. For the parameter isolation and expansion strategies, they preserve existing knowledge while expanding the model to include new data. However, they lead to increased model complexity and require extensive time for updates. They also struggle to reconcile new data with previously learned information effectively. In essence, while these strategies appear promising, they fail to fully satisfy the key requirements of streaming recommendation, effectively bridging the ever-present gap between evolving new data and past data distributions. It's not just about preventing catastrophic forgetting, but also about ensuring effective learning and adaptation to new data. This dual requirement is where these methods fall short. In order to tackle the aforementioned challenges, we draw inspiration from the concept of prompt tuning, a new transfer learning technique in the field of natural language processing. Intuitively, prompt tuning techniques reformulate learning downstream tasks from directly adapting model weights to designing prompts that instruct the model to perform tasks conditionally. A prompt encodes task-specific knowledge and has the ability to utilize pre-trained frozen models more effectively than ordinary fine-tuning. This effectiveness stems from the prompt's ability to add contextual layers to the model's understanding, thereby adapting its responses to new data without altering the core model structure. Moreover, prompt tuning stands as a data-agnostic technique. Unlike methods that heavily rely on the data they were trained on, prompt tuning can navigate across different data distributions without being hindered by the gaps typically encountered in evolving datasets. This quality makes it immune to the pitfalls introduced by the gap in data distribution. Therefore, the prompt tuning emerges as a potential solution for meeting the dual requirement of continual learning in streaming recommendation. It not only aids in preventing catastrophic forgetting by maintaining the integrity of the model's foundation knowledge, but also ensures effective learning and adaptation to new and diverse data patterns. However, applying prompt tuning in continual graph learning for recommender system is still a challenge. First of all, existing prompt tuning approaches are for data in Euclidean space. For example, the images, the text in the dynamic user-atom interaction graphs. However, changes are not just incremental. They are cascaded and interconnected, profoundly influencing the entire network. For example, the addition or deletion of a node would alter the states of an adjacent node and potentially leads to substantial changes across the entire graph. Therefore, how to disentangle the multiple levels of relationship changes caused by the cascaded changing of graph data becomes a unique challenge for graph prompt tuning. Furthermore, once these relationships are disentangled, a significant task remains in re-aggregating these representations while preserving the overall graph's integrity. Efficiently combining these decoupled elements is also vital for maintaining a coherent and accurate representation of the evolving graph. Then we will introduce our methodology. Here is the overview. We first disentangle the complex user-atom interaction graphs into multiple views, capturing specific interaction aspects. In continual learning scenarios, not only does the feature distribution changes as new items are generated and new users join, but also the edge information also evolves. For example, the user preference will shift during time. Therefore, both feature prompts and structure prompts are necessary. So we then design node-level prompts to focus on individual node attributes and structure-level prompts to address broader connectivity patterns. Afterwards, we propose the cross-view level prompts to aggregate information from these views, integrating new knowledge efficiently and adaptively. The user-atom interaction graph in recommender systems are inherently complex due to their dynamic and interconnected nature. When a new node is added or an existing one is removed, it doesn't just affect isolated parts of the graph. Instead, these changes can lead to cascading effects throughout the network, simultaneously influence multiple relationships and potentially reshaping the overall landscape of user preference and recommendations. In this context, we divide the graph into multiple views, where each view is tailored to capture specific aspects of the user-atom interactions. The disentanglement is achieved through a series of linear transformations. The linear transformations are capable of separating these views while maintaining the overall integrity of the graph. This means the model can isolate and focus on specific aspects without losing sight of the graph's interconnected nature. After disentangling the graph patterns into different views, we design node-level prompt to capture the comprehensive essence of graph patterns in dynamic recommender systems. The node-level prompts primarily target the attributes or properties of individual nodes within the graph. This could include user characteristics in the social network or atom properties in the recommendation system. By focusing on this level, the model can delve into the intricacies of node-specific data, allowing for a detailed understanding of individual behaviors or atom features. Specifically, for each view, the node-level prompts is a set of learnable parameters. These prompts act as targeted cues that inform the model about how to interpret and integrate new information regarding users or atoms. When new data arrives, these prompts effectively instruct the model by highlighting relevant features or changes in the user-atom interactions. Alongside the node-level prompts, structure-level prompts are designed to engage with the broader patterns of connectivity and relationship within the graph. These prompts are crucial for understanding and adapting to changes in the overall graph topology, such as the emergence of new interaction patterns or the evolution of existing ones. For each view, we design a set of learnable prompts for the edges that adaptively aggregate the structure-level information through the message passing mechanism. The integration of these prompts within each view facilitates a comprehensive and responsive learning process by simultaneously addressing both the granular details at the node level and the broader structural dynamics. Our model ensures a holistic understanding of the graph data. The aggregation of information from multiple disentangled views is crucial for providing a comprehensive understanding of the user-item interactions. If we straightforwardly aggregate the views through the attention mechanism, that may not fully account for the evolving nature of the user-item interactions, especially with the introduction of new data. As the graph's structure changes, the relevance of different views and their interrelations can shift, potentially rendering the existing fixed attention weights less effective. Therefore, we incorporate the cross-view level prompts for dynamic adaptation. This approach centers on updating a small set of prompts rather than relearning the entire model's parameters. These prompts serve as dynamic modifiers to the attention mechanism, allowing the model to adapt its focus efficiently. In this enhanced aggregation process, the prompts subtly adjust the attention weights, reflecting the current state and relationships within the graph. This strategy maintains the model's stability while enabling it to respond dynamically to new data, ensuring the final node embedding remains relevant and accurate over time. Next, we will show our experimental results. The dataset used in experiments are shown in the table. We adopt the 4 datasets which are commonly used in the streaming recommendation and their respective time span. We compared with the experience replay-based baselines, the knowledge distillation-based baselines, the parameter isolation-based baselines, and the vanilla fine-tune baseline. We find that fine-tune suffers from catastrophic forgetting as new learning overwritten previous knowledge, and the experience replay methods struggle to balance old and new data effectively. And our method achieves competitive performance compared to other continual learning methods. We conduct ablation study to analyze the effectiveness of different parts. We find that no node level prompt will decrease the performance significantly, and no structure level prompt results in a decrease in performance, but it's not as much as no node level prompt, and the cross-view level prompts have minor influence, which may be compensated by other prompts. We also illustrate the average training time per epoch of our method. We find that our method not only matches the efficiency of the fine-tuning baseline, but also outperforms several other advanced models in terms of training speed. This high efficiency can be primarily attributed to the use of lightweight graph prompts. We also studied the impact of prompt size. We find that initially increasing the size of these prompts generally enhances the performance. When the prompt size is large enough, we notice that further increasing the prompt size only brings marginal benefits. Moreover, excessively large prompts introduce additional computation overhead, which may not be justifiable given the marginal gains in performance. Interestingly, the optimal size of prompts also varies across different types. The cross-view level prompts require a larger size, while node level prompts are most effective with a smaller size. This variation can be explained by considering the nature of changes each prompt type addresses. The cross-view level prompts need to capture broader and more complex patterns of interaction across different graph views, which may necessitate a larger size for comprehensive representation. In contrast, node-level prompts which target more specific and localized information can achieve optimal performance with a smaller set of parameters. At last, let's make a recap to my presentation. For the streaming recommendation, we have the dual requirements. The first is prevent the catastrophic forgetting. And we also need to ensure effective learning and adaptation to new data. And we use adaptive prompts to modify data integration without altering the core model parameters. The experimental results show the effectiveness of our method. And at last, I'd like to discuss the difference between our method and model parameter isolation and expansion. Unlike model isolation expansion method, graph prompt tuning doesn't simply expand the model space to store new knowledge. Instead, it introduces a set of contextually adaptive prompts that act as cues for the new information. These prompts do not store knowledge in the traditional sense. They modify how the model interprets and processes incoming data. The prompts in our method provide detailed guidance, subtly adjusting the model's focus and understanding based on the current context. This is achieved without the need for extensive expansion of the model structure, ensuring efficiency and adaptability. The key here is adaptability. This allows our method to seamlessly integrate new insights while maintaining the integrity of previously learned information, therefore avoiding the catastrophic forgetting. That's all for my presentation. Thanks for your listening.